Hi everyone, my name is Tom Lee and I'm from QUANSER, and today I'm going to talk about engineering labs. Now many of you have been working very hard to come up with good ways of migrating your current teaching activities onto online forms, but let's face it, labs are a special breed of activities altogether. So we at QUANSER have been working with a wide range of institutions to look for different ways to in the short term respond to the current situation, but also to look for opportunities for refinement of teaching activities in general within engineering for the future. So a little bit about our company and what we do. QUANSER, the name is the combination of question and answer, and that kind of hints at our academic orientation. We're best known for hardware devices that go into research and teaching labs. Historically, the strength has been in control systems and control system validation, but more recently, we've been expanding into more contemporary application themes, autonomous vehicles, drones, like you see before you, and different types of robotics and such. So our background is very much rooted in the physical world, and we are at our best when we have walls around us and students are actually doing active things. But of course, we can't do that right now. So a lot of us have been talking about how to take the lab experience off campus. Now, before we proceed, it is important to clarify a few terms because we tend to use all sorts of different words to describe what we're actually looking for, and it's useful to think about that a little bit. So a lot of people use the word online for the form factor of what we're trying to deliver these days in terms of education. Now, I've seen many examples where people are doing some really good work with what they're calling online labs, where they're trying to deploy uh, many different types of software options or videos, or try to replicate the rhythms of lab exercises, but of course in a connected digital way. On the other extreme, the remote lab concept sometimes is used by people trying to actually connect to real hardware and control it in real time, and the information is observed by either video or data logging of some sort. So really actually doing labs at a distance. Um, and the difference between these two, one is definitely easier. Online, using just regular software of a simulation nature, it's a lot easier, but the experience is noticeably lighter than the physical counterpart. And the remote lab, although that's about as close as you can get to the real thing, of course, it's not that easy to set up. You're still dealing with issues of access of lab facilities and such. And in the end, let's face it, not all of the labs that we had in our programs were as modern as we'd like it. So any of the legacy issues that we face from those labs still persist within remote labs. There's a third category that we like to talk about at QUANSER, and we call that virtual labs. And in fact, this is not a new notion in terms of our definition of it. As early as 2000, we presented and published some concepts in what we called web labs. That is, doing activities that are very similar to what you would do in real life, but the actual observations, measurements, and renditions are made digitally over the web. And remember, back then, things like the bandwidth and everything was much poorer in terms of its ability to support different types of communication online. So we devised ways of implementing higher fidelity experiences, but still doing it over the web. And we call those virtual labs or lab virtualizations. So today, we're doing a bunch of different things with different institutions. And here's just a sample of the various directions we're heading. So top left is more of a core interactive lab that is students explore parameters and observe and measure the response in the system. And the visualization, as you can see, has a good deal of realism. And in fact, the dynamics are relatively close to the physical dynamics you'd get in a real lab. And so this is a pretty decent replication of the basic experience of physical systems. But beyond that, because we're in the digital world, all sorts of interesting things are possible. Different types of applications, environments, the way you actually engage in terms of exercises, all of those have much more opportunities for enhancements. We can also explore new frontiers like augmented reality, where the virtual world is engaging directly with the physical world and in some sense open up new avenues for us to explore progression of learning. We're sort of trying to do all of these things for a very simple reason. Labs in engineering are kind of important, right? So they're essential, but in terms of the engineering variety of education labs, there are some differences between what we do and what our colleagues in science or other places, other fields that have certain types of labs. There's a difference. And for us, it's not so much processes and lab procedures. It's really about the thing that we're working on. It's about devices. It's about systems. It's about applications. Currently, if you actually look at commercially available software options for virtual labs or online labs or any of that variety, if there are ones that are specifically geared towards topics, you tend to find them to be heavily influenced by the scientific approach, the science approach to labs, undergraduate labs. So this is new territory for a lot of people, and because of our background, QUANSER's background in the physical labs, and because we actually have a fair amount of software assets at our disposal, we started exploring a variety of different options. The first thing we did a few weeks ago was introduce something called the QUANSER Interactive Lab. And you saw a hint of this in the previous slide, but really it's the world's first and only dynamically accurate virtual lab platform specifically designed for engineering programs at the commercial level. So here you get a bit of a close-up look, and as you can see, and hopefully the video is coming through, the dynamics of the disc on the servo motor, it does look very realistic. And in fact, all of the results that you are seeing, including the noisy bits, we've put in a fair bit of effort to make sure that those are dynamically appropriate for undergraduate courses. So there's a whole range of different lab activities and specific exercises that are inherent in those, where students can step through. And what we've done with this particular iteration is pull together all those resources, develop the right type of user interface, and now it's in general release for the public. And for those of you teaching control systems, in particular the conventional controls course, the job is pretty much done now. You basically have to download and work with these modules directly as if they were physical hardware. We even have created a mobile app that allows you to do some of the preparatory work or reinforcement activities, or even some of the lab exercises in more micro form. And this is also a breakthrough because we do understand the difference between computers and phones as far as a young person is concerned, and we want to cover both bases. So this is a really tight and effective package for core control systems. And in fact, once we released this, within a week, we started seeing some videos and user experiences from faculty members around the world. And we stumbled across this video. Within a week, a professor had converted most of his course and most of his lab course and control systems using this technology. Now, in the end, I'm not showing the video because the video is basically a professor talking about a few things and showing a few things, and then students would follow and work on their own. So in general, the video isn't great, but just the notion that somebody was able to migrate very quickly with no help from us, that was very encouraging. So that was the start, and part of our strategy for the future is to migrate more and more laboratory exercises into this virtualized form. So here's just some samples of emerging QUANSER devices, which will be virtualized, and there's a broad range of applications that you can do with these. In fact, in some sense, once you're in the virtual world, and once you have the methodologies established as we've been doing, there's literally no end to the level of variations and imaginative applications of lab concepts. So this is just an animation that one of our engineers created. What it's meant to show is the sheer power of the visualization system. So we're actually using gaming software. That is the same software that developers use for the most powerful visual and immersive video games that you or maybe your children play. So the realism is quite astounding, and it has a reasonable level of, I guess, physics sensitivity to make sure the rendering of the movements are realistic. Having said that, those physics routines and the things that help us visualize the motion, it's not enough from an engineering point of view. So what we've done is we have matched that the basic visual realism with proper dynamically accurate mathematical models. And this is, again, part of our tradition at the company of creating hardware-based educational activities where we connect the concepts of the mathematics and the modeling and the analysis that we have historically taught in the courses with reality, with physical implementation and validation and the actual application-oriented contexts that are essential for real learning. So now we have a situation where we are trying to make all of those statements also true if you are in a virtual environment. So that convergence of the detailed mathematical dynamical models with physical realism in real time, meaning the time aspect is well managed, and even possibly through the magic of computer CGI style animation to start highlighting certain types of theoretical aspects above and beyond simple observation. And then you roll that into proper software framework so that people can connect to it using industry standard software platforms like the MathWorks or Simulink and MATLAB or Python or LabVIEW, what have you. And then you are providing a very modern approach to creating lab content. So instructors can now create their content on top of this, what is essentially virtual lab apparatus. And in many ways, they can approach it as if it was physical apparatus, except it, of course, is very flexible and students can access it anywhere, anytime. But also, there are opportunities to go beyond conventional labs and start exploring different workflows and different enhancements of the engineering and learning experience that will help us go beyond the constraints of traditional labs. So right now, this is one of the emerging workflows that we're aiming for within essentially the next month and a half, in time for the North American autumn semester. And this is a tight integration between one of the virtual labs and Simulink. So at least in this application space of control systems and control of physical systems, Simulink is a very powerful and industry standard, engineering standard software tool. And historically, when you are learning to design control systems, Simulink is one of those tools that become very handy. And what we've done was it integrated our virtual model within the essential Simulink workflow. In fact, as far as what students and users actually do with a Simulink, it's indistinguishable whether your final destination is a virtual plant or a physical plant. And because it's commercial grade software, we have a situation where everything is designed in a robust, scalable way and connects and integrates well to other types of software, like in this case, Zoom. So this was a little picture I took of a recent session that we had with some colleagues. So this notion of seamless software workflows with powerful contemporary tools, that's part of the key outcomes in this first round of activities. The other thing that's important is this notion of digital twinning. So that's a term that has been pioneered within industry, the notion of increasing in a very appropriate way the level of activity with high fidelity simulation and reducing the very expensive, time consuming, often dangerous activities with full physical systems too early in the progression. So in some sense, as much as we are responding to the current situation, we're also step by step bringing a modern workflow into the engineering lab. So there's a couple of core benefits there. In fact, in terms of workflows and what engineers actually do, one of the key things we're working on for the future is this notion of integrating projects. So it's one thing to do prescribed lab activities, and in fact, you can do many different things, regardless of whether you get as sophisticated as the QUANSER approach. In terms of projects, it's different though, because you do want there to be some type of a construction and design activity. And right now, to the extent that people can do projects, possibly sort of the leading edge of that are people who are or institutions distributing kits with relatively inexpensive, easy to use components that students can then create one thing or another. But in the end, because of the nature of those kits, you're going to be severely restricted in terms of what kind of applications and what kind of engineering you can actually experience. So to that end, we've worked on different ways to marry the higher fidelity model virtualizations and lab virtualizations with the same type of kit workflow that you might be interested in. So this is an example. This is actually a real example. It will be deployed at a real university in the fall semester. A myosensor, or it detects muscle movement, going into a bit of signal conditioning and ultimately into a microprocessor, and that microprocessor, using software that students would develop, will connect to a virtualized version of a robot. So you twitch your muscle or move your arm and the robot moves correspondingly. And that's sort of the foundational components of this project, this application project. So already you're at a level of sophistication that is far beyond what a simple kit on its own can deliver. The other good news is that the robot arm virtualization is based on a QUANSER commercial product arm. And if your institution actually has those in physical form, whatever you build and connect to these virtual arms will connect and work properly with the physical arm. So once again, there is this notion of the digital twinning, or efficiently using and harmonizing physical components with virtual components, and getting faster to design realization than was possible before. This project, or this example of a project, is part of a larger activity that we're currently doing with a university called McMaster University in Canada. And they have recently engaged in something called the Pivot, which is a full reconstruction of the first year experience, including the extensive project sequence that they have already had. And they really wanted to move to a next level of sophistication and modernization of projects. So we worked with them to create a comprehensive series of activities, culminating in what you're seeing here, which is an Industry 4.0 inspired application of multiple robots of different types and other types of machinery, all communicating with each other and using techniques of things like material sensing, sorting out items, and then taking them to, summoning the robots to take them to various disposable places. So this is different from traditional labs in that from day one, it is a complex, connected cyber physical application. And we have figured out or developed ways in collaboration with our colleagues at McMaster, student-friendly approaches to doing this. Now, this is not a senior level activity. This is going to be freshman level. Every kid who comes into engineering McMaster in 2020 would have experienced this with hardware. Of course, 2020 in the fall term in our country is going to principally be online. Thankfully, we had always envisioned a digital twin dimension to this, so we actually had the virtualizations ready to go. This course is actually in a pretty good place. Now, this gives you a sense of how sophisticated we can get on the application side, but we can go even further. So above and beyond robots that you kind of recognize, because of our experience at the company in the more advanced systems, in the autonomous system space, autonomous vehicles, this is our QCar, a new platform for self-driving car applications. These more advanced devices already come with a whole range of different virtualizations and alternate environment research and application potential. So this is just a simple example here of the car, which is heavily instrumented with all sorts of sensors and is really the world's only academically oriented platform for this type of application. And now we are trying to conceive of ways that this can also start impacting the undergraduate space to bring this type of activities into the undergrad program. And guess what? The virtualization is already done. So if all of a sudden we hit another situation where students cannot come to campus, they can still do very, very exciting and leading edge applications and projects. From a roadmap point of view, yes, this activity is now part of the strategic vision of the company, but we're kind of looking at it in two ways, which is we're going to have immediate situations to respond to before the end of 2020. And to that extent, we have aggregated all of our virtualizations and what we can do in a very short amount of time, working with various universities. We're creating commercialized and robust virtual models for some key items. We're calling the overall initiative the QUANSER Digital Transformation Program, because in the end, it's not so much responding to the COVID crisis, it's actually reconstructing the engineering learning sequence or engineering learning experience for labs that better reflect the modern applications and even modern workflows where digital has a much stronger role. So in a perfect world, you would have access to the hardware side on campus, but you would do a lot of virtual work at home or at a cafe or something like that. And the two would be integrated, just like what happens in modern industry. But in the long term, our intent is to grow the number of devices and virtualized systems and also applications and other ways and resources that faculty can fully deploy the full agility and flexibility of the virtual form. So that's called the QUANSER Digital Transformation Program. From a commercial point of view, it is rolling out within, well, it already kind of has, but very soon will be fully formalized as a subscription program. So institutions can sign on for a single annual fee. They get access to a range of different devices and specific resources and support from the company. And a lot of this really was the collaboration of the company using its technology in collaboration with universities and faculty members. We've been able to very quickly get to a state of providing some immediate relief for some very important topic areas, more so than if faculty were forced to just do their course and we have a massive divide and conquer approach. We're really trying to take things at a program level, something with a concept of platform and scalability. So the last video I'm going to show is a fun one. It has nothing to do with with actual engineering labs. But when we first encountered this powerful visualization technology, we saw some real potential, certainly in teaching, but we also know part of the appeal is the engagement factor and even entertainment. So one of our engineers actually put on his creative hat and produced the following video. You are not going to hear the music, but I imagine, if you will, holiday music. That is winter holidays that we have in North America, and all the bright lights and the sceneries that are associated with that. So I'll just play that, and hopefully you'll get a sense of the fun that you can have. So to conclude, I really did want to give you a sense of how our company is working to with our academic colleagues to deal with the current situation. So there is certainly a response element to what we're working on today. But the other part really is the work that we're doing seems to be pointing at some opportunities for innovation and to improve, COVID or no COVID, to improve what we can do, to modernize and to enhance and enliven the lab experience in undergraduate education. So there is an email address in front of you. My colleague Andrew Watchhorn, he manages the conversations that we have with the academic institutions. And if you have any questions on the work that we've been doing so far, please do not hesitate to contact Andrew, or me for that matter. So I want to thank you and hope to talk to you again soon.